Hello friends, welcome back to my channel. In today's video, let's discuss about nucleic acid quantification. If you are new to this channel, consider subscribing and click on the bell icon to get notified. Any experiment that requires the manipulation of nucleic acid mostly also requires its accurate quantification to ensure optimal and reproducible result. As you all know, the most of us use downstream application after the nucleic acid preparation, like PCR and cloning and other downstream applications after the extracting the nucleic acid. So it is important to calculate the concentration of nucleic acid we have to use in these experiments. The nitrogenous base positioned along with the nucleic acid strand absorb the ultraviolet light at a wavelength of 260 nanometer. At this wavelength, the light absorption is proportional to the nucleic acid concentration. This relationship is so well characterized that the UV absorption can be used to accurately determine the concentration of nucleic acid in a solution. So when you measure the solution, nucleic acid preparation solution at 260 nanometer, we can correlate the concentration of nucleic acid. The relationship between DNA concentration and absorption is linear up to an absorption at 260 of 2. So till absorbance 2, we can get a linear relationship based on the absorbance and the concentration. For measuring the absorption of nucleic acid solution in a spectrophotometer, the most molecular biology laboratories will use a quartz cuvette with a width through which the light beam travel is 1 centimeter. So the path length most of the laboratories use is 1 centimeter. As you can see on the graph on the right, you can see the linear relationship between the concentration of DNA and the optical measurement at absorbance at 260 nanometer. So how to determine the concentration of double-stranded DNA? This is very much useful when you are working with plasmids, genomes, etc. The quantification is typically performed by taking absorbance measurements at 260 nanometer, 280 nanometer and 320 nanometer. Absorbance at 260 nanometer is used to specifically detect nucleic acid component of the solution, and absorbance at 280 nanometer is used to detect the presence of protein. Because tryptophan residues absorb at this wavelength, so this can be used to detect the proteins. Absorbance at 280 nanometer can be used to detect the presence of protein. And absorbance at 320 nanometer is used to detect any insoluble light scattering components. And a spectrophotometer capable of providing a scan from 200 to 320 nanometer can yield maximum relevant information. So one can look at the spectra between 200 to 320 nanometer and can get a fairly good idea about the purity and the presence of contaminant in the DNA prep. For nucleic acid purified from biological source, calculating the ratio of the reading obtained at 260 and 280 can give an estimate of how pure the nucleic acid preparation is. Pure DNA free of any protein contamination will have an A260 by 280 ratio of 1.8, and if the preparation is contaminated with phenol or protein, then the A260 by 280 ratio will be less than 1.8. And if RNA contamination is present, if RNA is coming into the DNA prep, then A260 by 280 ratio may be greater than 1.8. And for the pure RNA preparation, the A260 by 280 will be close to 2. At 260 nanometer, the DNA concentration as low as 2 microgram per ml can also be detected. And a solution of DNA with a concentration of 50 microgram per ml will have an absorbance at 260 equal to 1. So 1 OD, suppose if you measure the solution and you get 1 OD, that corresponds to 50 microgram of DNA per ml. So using this, we can calculate the concentration of DNA. As you can see in the graph, based on the peak, we can get a peak at a different wavelength. We can fairly say how good your nucleic acid preparation is, or how pure the nucleic acid preparation is. The extension coefficient for 1 millimolar solution of DNA, double-stranded DNA, is around 6.7, and this can be used to calculate the molarity of solution of DNA. Coming to the single-stranded DNA concentration, as we mentioned, the 1 OD of double-stranded DNA corresponds to 50 microgram per per ml of the DNA, whereas 1 OD of single stranded DNA will corresponds to 33 microgram per ml. So suppose if you want to determine the concentration of high molecular weight single stranded DNA in picomole per microliter. So this can be calculated by first calculating the how many micrograms of single stranded DNA are present, and then we can convert that to picomole per microliter. So the concentration of high molecular weight can be expressed as picomole per microliter amount by first determining how many micrograms of the single stranded DNA that are equivalent to 1 picomole. To do this, we can use the average molecular weight of the deoxynucleotide in the DNA strand. For single stranded DNA, it is taken as 330 Dalton, and this value is then used to convert and bring the concentration of single stranded DNA expressed as microgram per ml to the concentration expressed in picomole per microliter. The extension coefficient of 1 millimolar solution of single stranded DNA is 8.5, and this can be used to calculate the millimolarity of single stranded DNA. And the extension coefficient of DNA is 6.7. Double stranded DNA is 6.7, and this can be used to calculate the molarity of the solution of DNA. Hope you're clear with this topic. If you like the video, please press the like button and share it with your friends. Thank you.